Welcome to this Frequency Matters podcast. I'm Pat Hindle, and I'm here with my co-host Eric Higham. Today, we're talking with Sundeep Rangan. He's the professor of electrical engineering at New York University and also associate director at NYU Wireless. And we also have Bryan Goldstein, corporate vice president at Analog Devices. Welcome, Sundeep and Bryan.
Pleasure to be here.
Good morning.
So NYU Tandon has been collaborating with some institutions and industry partners, including Analog Devices, and has been awarded close to $10 million to develop next generation communications technology. The project is dubbed SALSA, which is short for Spectrally Agile Large-Scale Arrays, and it's funded by the U.S. Department of Commerce's National Telecommunications and Information Administration. And its goal is to advance U.S. leadership in open, secure communications infrastructure. So that was a lot to say in one sentence there, but maybe you can tell us a little bit about, what is the goals of this project and how it's going to be structured. Maybe Sundeep can start out with that.
Sure. So it's a pleasure to be here. So the project was really motivated by two goals looking at cellular wireless infrastructure. The first is what you could say is spectral agility. So today's wireless infrastructure typically operates in exclusive spectrum that's allotted and fixed over time. What we wanted to do here are look at systems that are more spectrally agile. That means that they could detect dynamically which are the right frequency bands and also frequency hop among those bands. And that was particularly motivated by our earlier work, including our NTIA NOFO 1 project, which looked at the upper mid-band. And I know a number of your listeners are interested in these upper mid-band, sometimes called FR3. And we're looking at specifically the bands from 6 to 15 gigahertz. And that's an interesting band because it offers a lot of opportunities for cellular services because it's a good mix of balance and coverage, but it's also used right now by things like satellite services. So things will need to be more spectrally agile. I'm sure we'll talk about this more in the podcast. The second feature that we really wanted to address is scalability. So one of our partners, Nokia, who's on the grant, I'm sure we'll talk about that as well, already sells base stations today with about 64 MIMO streams, 64 digital streams. But this will have to likely already scale to 128 or 256. And if we want the features of full spectral agility, maybe even scaling to the order of 1,000. And that's technically very difficult. So broadly, the project is trying to develop these scalable, spectrally agile, large-scale arrays that can address these potential future needs. And that's where we got the acronym SALSA.
So those are some pretty ambitious goals. And what are the main tasks that you're going to implement to try to achieve those goals? And what's the timeline for those tasks?
Sure. So the overall project's about 5 years. So we have a little bit of time, but that's why we were taking something that's a little ambitious so that we would come out with something at the end of this that would potentially be commercially interesting. So we kind of break it up into 4 key tasks. The first and the main part is really building an RFIC for a spectrally agile system. And what that RFIC would have to do is be wide bandwidth and also with the antenna systems there to make them wideband and spectrally agile, meaning that it can quickly switch in frequency. The second part of the task is to build MIMO platforms around this. And probably within the budget of this, even though it's a very large project, we want not likely to build a commercial system by the end, but we want to be able to get actual MIMO systems that have a fair number of elements, say at least in the order of 128, out to customers at a reasonable cost. And that means that with this, customers, potentially research labs, maybe some of these labs that are in your companies, if you're listening to this, or at a university, could actually start to run experiments and build prototype systems around that. The third part of that is to take these MIMO platforms and then integrate them into an Open RAN framework and testbed. And we have some excellent partners, for example, at Rutgers University, which is a specialist in this area. Open RAN, for those who don't know, is a new architecture that's being proposed for the radio access network. It was previously monolithic, so you would get all the components of that radio access network from a single vendor. Here, it's broken up into various pieces, and this could be what's called the Open Radio Unit. This is a very exciting development for this type of project because it allows smaller third-party vendors to enter into the cellular market, where there was previously a high barrier to entry. And then finally, we want to demonstrate some key applications on this. And we're thinking things like both adversarial scenarios, where you're in a hostile environment and the system is actually under attack. Hopefully that won't happen in the US, but it could happen in, say, some of our allied countries where we deploy networks, as well as systems where maybe commercial systems where we're just trying to coordinate with other cellular providers or with, say, cellular satellite.
And so Analog Devices makes a ton of products in this area, Brian. So what is your involvement here and what are you going to contribute?
Yeah, thank you. So we've been engaged with the ORAN Alliance since the founding meetings in 2018. And we continue to work in several of the working groups. We're involved in looking at the front haul interface between the distributed unit and the radio unit. We're looking at network security and also the radio hardware reference designs that are enabling these demonstrations. And that's a big part of our play on this program. So we're gonna provide the ORU platform and the interface from the MIMO software-defined radio to the front haul interface that talks to the higher protocol layer of the open distributed unit. We're gonna leverage our knowledge to ensure interoperability of all these pieces as they come together. And so specifically, we're going to be providing the 8ARB 904X software-defined radio transceiver that can transmit above 7 gigahertz. And on the baseband side, we're connecting to an FPGA that's going to include the lower 5 functionality and the ORAN IP that carries all the control, synchronization, and management plane messages. We also are providing the precision time protocol through synchronization plan and through the RAN components. So what we're doing is we're providing the basic software-defined radio, but also how to integrate it. We're providing an ORAN test bed of this all put together. So a lot of this work has already been put on a nice demonstration platform, but we're bringing the domain expertise as well. So when we fully integrate the digital front end, which maximizes linearity and emissions performance, we're also looking at the complete signal chain and the overhead of power consumption. And that's a big part of this, as well as how do we drive down and make these radios more efficient. The other thing that we're bringing is digital pre-distortion and linearization algorithms, and which combine crest factor reduction algorithms so that we can improve efficiency. So we're doing a lot, not just at the radio, but through software and algorithms so that we can help Sundeep's team put this all together quickly.
Yeah, great. Thanks, Brian. It certainly sounds like there's a lot of activity going on and global implications without a doubt. What other organizations are involved and how will they be contributing?
Yeah, but just before going to that question, I just want to say Analog Devices has been a great partner. They were a partner in the earlier version of this grant, and that's where we actually were able to get a first use of their ORAN platform. And of course, Analog Devices just brings enormous knowledge in the area of RF. Now, we've had some other fantastic partners as well. I think the most important is a small startup that came out of NYU, Pi Radio, whose founder was Aditya Dhananjay. He was my former PhD student, so full disclaimer. And but they actually were the partners in the earlier version of this grant. And what that grant did was build a COTS version of this device. Now, that was actually built with Analog Devices integrated circuits, and that was a sort of first FR3 radio. But because it was COTS, it could only have 2 channels, and it was relatively bulky. And but we had an enormous amount of interest from researchers and other companies to try to get hands on this platform so that they could start their experiments. And that's what really motivated us to take that platform, and what Pi Radio had done is to create an RFIC version. So that's one partner. The second partner, in addition to Analog Devices, is Princeton University. Princeton University is specifically Kaushik Sengupta is a fantastic RFIC circuit designer there who's worked with many of these companies in the past. And he'll be building most of the transmit side of the RFIC, along with a professor at NYU that we recently hired, Hamid Rahmani. The third person is Rutgers University, specifically Ivan Sesker. They have he's probably the world expert in ORAN, at least within universities. He runs an entire ORAN testing center and has, if you're ever in New Jersey, please check it out. It's a fantastic lab. And we're going to be doing a lot of the testing there and the integration and showcasing. So some of our demos might be in their New Jersey facility. And finally, not too far from Rutgers is Nokia Bell Labs, and particularly Jinfeng Du, but also the overall organization run by Amitava and Amitava Ghosh. And they're looking at just at least studying, trying to basically set the requirements and evaluation for this to make sure that this has a commercial path to a tier one vendor.
Great. Yeah, I saw a lot of those companies at the Brooklyn 6G Summit. I remember Pi Radio and
Yes.
ADI. Nokia is always a big supporter there. So, we talked a lot about this is focusing on the mid-band frequencies, upper mid-band specifically. Why is that an important area for FR3?
Yeah, so there's a lot of interest. I think to see the interest in FR3, you have to see it in the context of the developments at the frequencies that were both below and above it. So if you look back at the, say, spectrum landscape circa 10 years ago, most of your cellular surfaces, actually all your cellular surfaces, were in what's now called FR1, or even a smaller slice of FR1, typically below about 2.5 gigahertz. But of course, the spectrum was very congested there, and that led to a lot of interest switching way up into the millimeter wave bands. And commercial networks came out at, say, 28 and 37 gigahertz in the US. And to date, that has been a technical success in the sense that you do get very high peak rates on your phone. Something like about 1.6 gigabits, I think, is the average data rate. But this coverage is very, very spotty, as many of your readers or listeners will know. The upper mid-band is really this spectrum between FR1, meaning the sub-6, and FR2, meaning the frequency range 2, meaning the millimeter wave, and FR3 is that area in between. And it's thought to be, Nokia uses the term, I think, the golden band, because it's kind of a good mix of getting the higher spectrum that you have in the millimeter wave, but with potentially favorable propagation. But the downside of that is that unlike the millimeter wave bands, which were relatively virgin and unused, there are a lot of incumbent technologies, particularly satellites in these areas, but also important defense systems and astronomical systems. And so we will need to somehow figure out a way to coordinate that. And that's what part of this technology that we're hoping to develop addresses. I think Brian might have, because I know ADI has also been looking at this.
Yeah, no, you said it well. I'll just add a little bit on some of these other applications. So we're going to be, the good news is that because there's other applications, there's a lot of technologies being developed in these frequency bands. So that's a good thing. Also, having understanding of all this other applications that will be perhaps cluttering up the spectrum, we need to be aware of. And so understanding what's going on in the SATCOM realm, as well as different radar bands through military and commercial applications, is going to be important as we're building out frequency plans and making these networks viable.
Yeah, interesting. So if we dig a little deeper into the technology and application weeds, what are spectrally agile large-scale arrays and how do they work?
So what I think the way that we're thinking for the architecture, one aspect of this, well, let's start first with the RFIC. So what we need on the RFIC and the antenna systems are things that operate very wideband. For the RFIC, we think we have pretty good designs already, and other people have demonstrated these that can operate fairly wideband with a fair amount of linearity. And linearity is important because we want to have something that can operate dynamically with disparate signals. The wideband antennas is a little more challenging, at least to get that into a compact form factor. So some of the things we're doing here are things like tightly coupled arrays. and potentially some types of antenna switching, but also some interesting designs for the antennas. When you go to the large scale aspect, this also becomes challenging because how do we ever process, say, 1,000 elements? Clearly, we can't process that on a single IC. So we need an interesting, kind of flexible and modular tileable structure for that. So we're thinking of RFICs that maybe support 8 to 16 channels each. And then those go into an array of processors. And we basically have relatively clever algorithms, we think, to try to distribute that processing over a number of baseband chips. The key part there is to maintain the frequency coherence, but we can do that with, say, just a correct LO distribution. So that's at a technical level, I would say, how we're trying to address this.
And so what new technologies will be needed to realize the arrays other than the antennas you talked about in the RFICs? Is there other technologies needed?
I think the big thing, in addition to those two, will be all the digital processing, because we'll have to really think about, when you start to do things, there are two things that make it different. One is just simply the scale. So we're talking about doing, say, MIMO processing over 1,000 elements, and that becomes very computationally challenging. I mean, we know the math formulas, but when you try to translate that into what we need to do in practical hardware, we have to think about algorithms differently. But we also have to think about a lot of other functions that we haven't had to do in commercial exclusive license spectrum. So things like very high accurate localization, fast spectrum sensing, and also dynamic algorithms to switch the bands. And these are all algorithms that we hope that this can provide a platform at least to start developing, because once we have the RF around this, we'll be able to develop these.
So switching direction just a little bit, ORAN has been mentioned a couple of times in the discussion. Why is ORAN important for this project, and what specifically is Analog Devices providing in this area?
So let me just take a first crack, and then I think Bryan, because Analog Devices has been working a lot in the ORAN area, will be able to comment more. But let me just say from the university or a startup perspective why I think it's interesting. I think I mentioned before, the cellular markets have generally been pretty high barrier to entry for smaller companies and also for university researchers to be able to get into. And that's because the technology typically was monolithically sold. So a very experienced provider like Ericsson and Nokia would sell the operator, a monolithic base station, which they're very high quality. But the problem is that if you have a advancement in a part, it really wasn't easy to integrate that without a lot of collaboration with one of these vendors. One of the things ORAN does is it splits that functionality up. And for example, these salsa arrays, or maybe some derivative of them, potentially could be integrated as one of the components in that, while working and getting the benefits from all the other components that a commercial vendor like Ericsson or Nokia would develop. So that's one of the things that we're kind of quite excited about in terms of ORAN.
Yeah, no, from my perspective, I think ORAN it's critical to allow faster innovation in this market. Like Sundeep said, it's been a high barrier to execution with relatively few players, each doing their own locked ecosystem, and that can stifle innovation. Where ORAN now is creating an open set of specs that more companies are allowed to get involved at different pieces of the system. And as far as ADI, we're proud that we're developing the transceiver as part of the ORU architecture. And again, we believe that ORAN is going to play a very, very important part of the future in enabling future innovation. And we also believe that ORAN is going to allow Sundeep to really accelerate the adoption of this salsa technology and these platforms, because the open architectures are going to allow this stuff to find many more homes in the future.
Bryan, I think you and I maybe mentioned this at Mobile World Congress, but there was a lot of excitement about ORAN in the beginning, and then it seemed like it kind of like died off a little bit. But is it coming back around now because of 6G and other things?
Yeah, well, I'll tell you, it's hard to tell a little bit in that because the market is in the state that it's in right now. We were at my Mobile World Congress, and it just feels like everyone's sort of sitting and waiting a little bit to see. But I could tell you our most fruitful conversations there were around ORAN. There are some of the bigger network providers that believe in it and are investing in it and starting to put open ORAN pieces into their networks in early stages. So I think it's very important. I think the market's in a place where it's hard to tell what's going to happen, but I believe that over the next year or two, we're going to start seeing the market come back, and you're going to be hearing more about the ORAN because there's just so many companies that are investing right now.
And so another goal of this project was to make systems more energy efficient and secure. And so how will that be accomplished? What are some of the areas you're looking into?
Yeah, so in the transceiver itself, which is one of the power areas, and then of course power amplifiers are another power area, and then the last is in the processor. From our perspective, we're starting to put features and algorithms within the transceiver itself so that we can have things like discontinuous transmission where we can automatically turn on and off some of the power consuming areas of the radio. We can turn them off when they're not needed. We're also integrating media access control security and providing encryption and security to the data link layer over the front haul interface. And so being able to do more of this integration in one place and using energy consumption as one of our top specifications has allowed us to really bring down the levels compared to past generations of our software-defined radios.
And what about security?
Well, one of the things that spectrally agile systems can offer is better resistance to, say, for example, jammers, because of course one could detect jamming signals and then potentially try to hop around them, or maybe provide nulling. So we think that one of the potential areas for this, the DoD in the US has been interested in, for example, secure 5G and basically making this system more resilient. So that's I'd say one of the key drivers that we have in looking at spectrally agile systems, in addition to the commercial benefits.
So we've talked about a lot of technologies and needs that this project will be addressing. What do you see as the future for the technologies that will be developed during this project?
Yeah, I'll just go first. From our perspective, we're looking at both the comms and aerospace and defense markets sort of in parallel. And so a lot of these technologies overlap, from the high-speed converters to the digital ASICs and FPGAs, all the way through the RF signal chains to the antenna and the antenna beamforming and phased array technologies. And so a lot of the work that we're doing for ORAN also applies for work that we're doing in MILCOM and SATCOM, as well as radar and surveillance and countermeasures types of things. And so we're investing throughout. And so we're spending a lot of money on our software-defined radios. We believe chiplets, in terms of breaking up these software-defined radios into building blocks, is a way to accelerate the technology advancement as well as lower the overall investments on individual pieces. We're building all the RF signal chains for all the different frequency bands and applications that are out there between the two markets. And same with beamforming technologies and power amplifiers and low noise amplifiers. We're trying to cover all of the different frequency ranges and application requirements between military, defense, and satellite and commercial communications. But we're also looking at higher levels of integration and how do we bring these pieces together and provide more value to our customers by taking more of the load off of their hands through doing more applications and allowing them to focus on more of the network and systems needs and the software needs from their side, and we're taking on more of the hardware burden.
Well, maybe I'll just quickly add a little bit to that. what I just wanted, I think we're looking at really from two perspectives from our terms of for commercialization. This grant was part of the program, and we're very grateful to the NTIA for the opportunity to work on this, was to try to get commercial value. And what we presented them was sort of at least two or three tracks. One track of this is that a lot of researchers, simply the effort it takes, even if you were to able to get the RFICs for this, to actually build out an entire MIMO platform is a huge amount of work. And what we're hoping is to give kind of a turnkey solution that somebody can have that MIMO platform with a reference design that will be able to start innovation in this space. And we think that's certainly attractive for a lot of researchers as well at universities, but also potentially startups. Even if, larger companies typically have the resources to do this, but for other companies, this is not a possibility. But in addition, of course, to realize that we wanted to build that RFIC, and that RFIC, we think itself could be of value because right now, at least, there's not that a number of high channel FR3 systems out there commercially. So this can also be marketed.
Well, it's all interesting stuff. So thanks, Sundeep and Bryan, for
Thank you.
talking with us today about this next generation communication technology project funded by the NTIA. Certainly best of luck with the project, and we hope to follow up with you after some of the projects are completed. And to our listeners, please give us a like and subscribe to this podcast. And you can find more podcasts at podcast.microwavejournal.com. And thanks for listening.